Hey class, Mr. Moynihan here. Hope you're doing okay. Time for our second lesson, this time on transformations. So moving away pretty completely from trigonometry. Last time we had a lesson, we learned about vectors, which had some trig involved. We're going to be using vectors in this particular unit on transformations. Let's take a look. Last semester, around December, one of the last things we learned last semester was a related skill, which was to identify transformations, where I would give you two shapes already drawn or printed, and the task was to figure out what kind of action caused these two shapes to occur. Was it a slide, a translation, a flip, a reflection, or a turn, a rotation? And you had to give some detail about how each one of those shapes were, or those motions were performed. A vector of translation, a line of reflection, or an angle of rotation. We also watched a pretty fun video, if you remember, of the Ohio State Marching Band doing transformations in their video game halftime show, which is pretty awesome. Our new skill this semester is not identifying transformations, but rather creating them, being able to make them on our own. And that's a little bit harder. When we say transformations, what we're referring to are these four kinds of motions. I'm going to start with translations. A translation is a movement along, or a slide rather, along a vector. Some vocabulary here. The blue image in all four of these is going to represent the pre-image. And the red in each of one of these is going to represent the result, the image. So we go from pre-image, original, to image, the new. So a translation is just a slide, horizontal, vertical, some combination of left, right, up, and down, maybe multiples of those. A rotation is a turn, you probably know that, around a fixed center of rotation through a given angle, 90, 180, something like this, in a certain direction. So you can't just say a 90-degree turn. You got to say 90 counterclockwise or 90 clockwise. Direction matters significantly. So this particular one way to figure out the kind of rotation that it is to connect corresponding vertices to the center. And that looks like it's roughly, if I drew that better, probably closer to a 90-degree angle. And it's moving in the counterclockwise direction. So we would say this is a 90 degrees counterclockwise rotation around this fixed point of rotation. We also talk about reflections. A reflection is a flip, pretty straightforward. More specifically, the reflection, the line of reflection, I should say, is always the perpendicular bisector of the segments whose endpoints are corresponding vertices. That's a lot of word soup. So what that really means is the line of reflection is always cutting in the middle at 90 degrees, all of these horizontal green lines that you see here. Could be vertical if it's tilted. Another way of saying this, maybe even more straightforward, is, and this is important, that every point in the reflection is the same distance on the other side of the line. Every point in the reflection, the image, is the same distance on the other side of the line. So keep that in mind. So I skipped over dilation because these three are in a category called rigid motions or isometries. Those are, again, these three are motions that maintain congruence. They make identical figures. The only one that's sort of an oddball is the dilation, which makes similar figures. So the pre-image blue and the image in red here in dilations, these are similar or proportional figures. Dilations also require a center of dilation, much like a rotation does. And the center, you also have to have a scale factor. How much bigger or smaller is the new shape going to be? So let's start looking at each one of these in some more detail, starting with the translation. I had to make a modification here from my printout. The translation, we're going to learn all of these actually just by kind of doing a couple problems and figuring out how to do these as we go through them. The image of point A after a translation left 4 and up 3 is the point A prime, negative 4, 5. Determine the coordinates of the pre-image point A. Let's go ahead and plot where negative 4, 5 is in the first place. That's this dot right here, and we're going to call that point A prime. Keep in mind, this is the image. The image is that. Our task is to find the pre-image, the original point before it moved. So the translation that created A prime is a translation left 4 and up 3. So getting here required moving through that vector, left 4 and up 3. In component form, that vector would be this, change in x and change in y. That's the vector component form of what's being described in verbal form there in black and blue. So let's do that backwards to figure out what the original point was. Instead of going left 4, if we work backwards, we would go right 4. So let's do that from where we are. So going right 4 spaces would take me to the y-axis, it looks like. And moving up 3 is what happened. So working backwards, I should move down 3. So that would take us to right here. So this point, 0, 2, should have been the original point A. Let's check to see if that's right. From there, if I go left 4, 1, 2, 3, 4, okay, and up 3, 1, 2, 3, hooray! That vector would indeed take me from pre-image to image. So my final answer is 0, 2. Kind of a similar problem in some ways. For the second one, the image of the point 2, -4 under a translation, and notice it did not give us what that translation was. The image under a translation is -4, 1. Let's stop right there. Let's figure out which one of these 2 points is the image and which one is the pre-image. The word pre-image does not appear in the problem. So grammatically, this says that the image of the point, so this is a prepositional phrase, the subject is image, the verb is, and the object is -4, 1. The image is -4, 1. So that's going to be my new point. -4, 1 is where my point ends up. That's going to be my image. Let's call that point B prime. That means my original point, of course, was called B. Prime is the new shape, recall. So where was the original point? 2, -4. The image of 2, -4 is -4, 1. So 2, -4 is right here. So that's my original point B, and this is my new point B prime. So the vector that creates or that connects these two is going to be my translation that, let me draw that better. The translation that is also going to be applied to a third point. So let's find the components of this vector. So this is the translation that we just made. The components of this vector have a horizontal motion of, let's see, 2 and -4. That would be going left 6. So left 6. And looks like I'm going up. My old y coordinate was -4. My new one's -1. So -4, -1, I went up 3. So this is my translation right here. My new point that I'm going to translate, let's call that point C, is -5, 3. So -5, 3 is right here. This final answer that we need, find the coordinates of the image of -5, 3 under the same translation. So we have to apply the same rule to our third point C. Well, how do we do this? Well, I could just graph it and go left 6 and up 3. I could do that. There's a problem from this picture that I've given you, though. If I go left 6 from where C is, I'm going to fall off the grid. Moreover, if I can come up with a numerical method, maybe I don't have to draw a picture every time, and it's faster to not draw a picture if I can think about it. So if I'm going left 6 from -5, I should end up at, right, -11, because I'm taking away 6. I'm basically adding these numbers together, right? This is the same idea of adding vectors, or similar to adding vectors from before. So this would be -11. And then the y value was 3. That's where I am right now. I'm going to go up 3 from there, so I should end up at 6. Oops, not a vector. So So my final answer would be negative 11, comma 6. Doesn't fit in the picture, but if you visualize doing the same action with this purple arrow, you can see that I would end up somewhere in the neighborhood of negative 11, comma 6. I don't know why my video is quite so laggy. Okay, translations. Reflections. Rather than explain this in a number form, we're going to look at a picture. So let's switch over to Delta Math here. So we're given this the shape, and it says reflected across x equals negative 1. Remember earlier I described that reflections have the new point the same distance on the other side of the line as the old point. So all we got to do is go point by point with this triangle and plot each new one the same distance across the line on the other side. So for example, this point is 2 spaces away from the line. So I'm just going to go 2 spaces on the other side. Hey, that point's done. This point here is 1, 2, 3 spaces away from the reflection line. So I'm just going to go 3 spaces on the other side. And over here, I have a value of 6, a value of negative 1. That should be 7 spaces, and you can count it out if you want. If I go 7 spaces here, I should end up at negative 8. How's that look? Pretty good. Let's find out. Hey, not bad. And pretty nifty animation to show how it works. Let's do a different one. Let's try this one. Reflect across y equals negative 1. So same deal. This point is 1 below the line, so my new point's 1 above. This point is 6 below the line, so 6 above. You can count and make sure. This final point here is 2 below, so 2 above. Looks okay. Fingers crossed. I knew I was right because I thought about it and I was careful. But if you make mistakes, it's okay too. You learn from mistakes. So reflecting across the line, pretty straightforward as long as you're careful about counting. And one note I'll make here, if the shape happened to cross through the line of reflection or the line crosses the shape, then you're going to get sort of an overlap. So imagine for a moment if I was reflecting across, if I brought this blue line down horizontally here, like across the pink shape, then the shape would kind of flip-flop on itself. We'll get more into that later. Okay. Now, there are certain rules for reflections that can make things a little more straightforward when you have only a point and not like a whole picture. So here's a couple important rules to know. If you reflect a point across the x-axis, the x value does not change. So when you reflect across the x-axis, the x value does not change, the y value becomes the opposite. So for example, if I were to flip this point right here in red across the x-axis, the x value would still be 3. The y value would become negative 2, right? So what do you think the rule for y-axis is going to be? Well, hopefully you're right. The y value stays the same and the x becomes the opposite. For example, this point right here in green, to flip it across the y-axis, which is right here, would simply be to flip it across over there. The y value too remains constant, the x value becomes the opposite, which is exactly what this says. Now these next two are a little bit trickier. The line y equals x, represents this line with a slope of positive 1. And if you reflect something across this line, it can be a little more complicated to figure out. The good news is, this equation gives you the rule. It says, in English I guess, y is x. So the original point, x comma y, well this equation says y is x. Another way of saying that is, well, x is y, going in the symmetrical opposite direction. So x and y are literally going to swap places. So this becomes y comma x. For example, if you had the point, let's say 3, 1. 3, 1 is right here. According to this rule, this says swap those numbers. So not 3, 1, but rather 1, 3. So 1 comma 3. You'll notice I flipped directly across that diagonal line. So it works. Finally, we have y equals negative x, which is this line right here. It's a negative slope diagonal passing through the origin. Well, much the same, this tells you what to do. The rule is take your old point, the y value, that's going to be negative x. So the x value will be negative y. It's another way of saying the same thing. Let's do one test example here. Let's say I have the point 3, negative 1. 3, negative 1 is right here. If I flip that across the orange line, it should end up somewhere over there, just visualizing the way it should flip. The rule here says swap the coordinates and make them negative. So currently it's 3, negative 1. So if I swap them, it becomes negative 1, 3, but then change the signs. So 1, negative 3. Hey, what do you know? It works. So make sure you know these rules. Very handy. Finally, we have rotations. And rotations are, rotations, sorry. Let's take a look at these real quick. What's the reflection of 2, negative 3 over the x-axis? Well, hopefully you remember the rule. The rule says keep the x value what it is and change the y to the opposite. The good thing about knowing these rules is there's no need for a picture, right? We can make sure it works. 2, negative 3 is here. Flip it across the x-axis, and 2, 3 is there. So hey, it works. Great. What is the image of negative 4, 1 after a reflection across the line y equals x? Well, if you remember the rule is just swap the coordinates. X is y is x. So the answer should be 1, negative 4. And guess what? It is. Finally, rotations. Rotations are maybe the hardest of these three. People tend to differ, but it's one that traditionally gives people some trouble. Part of the challenge with rotations is there are rules you kind of have to know going in. They deal with the fact that slopes that are 90 degrees, perpendiculars, are opposite reciprocals. So you're going to see some opposite positive negatives and some switching happening. So let's go ahead and go over what these rules are. The rule for a 90-degree counterclockwise rotation, 90-degree counterclockwise, is this. You take the old coordinate, xy, and it becomes negative y, comma, x. For example, if I had the point 1, comma 3, if I'm rotating that 90 degrees counterclockwise, which quadrant 1, 2, 3, or 4, if I rotate that point 90 degrees counterclockwise, which quadrant will it end up in? Well, it should end up in quadrant 2. Specifically, if it's a 90-degree angle, it should end up somewhere over here, 90 degrees. So the coordinates of this point are 1, 3. The rule says make it negative yx. So negative yx here would be negative 3, 1, based on this point. And you can see that would work. If I plot that point, you'll see that it creates a 90-degree angle with the origin. So it's a rotation of 90 degrees counterclockwise. A 180-degree turn is actually pretty easy. We associate 180 sort of in culture with oppositeness, right? Opposite direction, 180-degree turn, full rotation. So the only combination that we haven't really done yet is making the coordinates the opposite. And that's it. One test case, let's say I have the point 4, 1. If it's turning 180, it's going to turn a half rotation, half rotation around. So it's going to look something like that, somewhere over here. It should go to the third quadrant. So 4, 1, according to this rule, would be -4, -1. And here you can see we would have done a 180 to achieve that. Finally, 270 counterclockwise is 390s or 190 in the other direction. So 270 counterclockwise is the same as 90 clockwise. The rule for a 270-degree counterclockwise rotation, is this. It's very similar to this with a minor change. Y -x. Let's close out with some examples. What is the image of the point 4, -3 with a 180-degree turn? Well, if you remember the rule from the last slide, the rule for 180, and this is why knowing the rules is so important, makes it really easy, is just make the coordinates the opposite. So currently I have 4, -3, plugging them into this pattern, -4, and what's -3? There we go. Done. Easy. No picture necessary. Finally, what is the image of the point -2, 5, 90 degrees counterclockwise about the origin? What's the rule for that? Oh yeah, the rule for that one is -y, x. So plugging in my coordinates, -2, 5. Okay, gotta be careful here. -yx means I'm gonna swap my coordinates, right? So let me go ahead and do that first. 5 here, -2 there. The y value, which is in the x position now, gets an additional negative. So my answer should be that. I'm not too sure about this because this is a bit harder, so let me graph it and kind of see. My original point was -2, 5. So -2, 5 would be right here. If I turn that 90 degrees counterclockwise, it should end up in the third quadrant. It's going from here to there. So -5, -2. The answer that I think is correct would end up here. The way to check to see if these match is connect both of them to the origin and see if you get a 90-degree turn. Looks like we do, and I'm going from here to here, so it checks out. All right, that wraps it up for today's video. Hope you are doing well in your quarantine. If you have any questions, of course, I'm available for help, and I will see you later. Take care.